So here we get a question from JEE Mains 2020, and the topic from where the question is, it's from gravitation. So let us see, it's a very beautiful question. Let us see what it is. A satellite of mass m is launched vertically upward with an initial velocity u from the surface of the earth. So suppose this is my earth of radius r. So from the surface a satellite is launched with velocity u. Let us say this point is 1. Okay. After it reaches height r, suppose there is some height r. Okay. This height is r. So at this height there will be some orbit. Okay. At height it ejects a rocket of mass m by 10, so that subsequently the satellite moves in a circular orbit. So at this point, suppose this point is 2. At this point the satellite is going to move in a circular orbit. So it has this tangential component, and we know this is orbital velocity. The orbit, this one. And the orbit is at a distance of 2r from the center of the earth. So we know the orbital velocity is equal to gm by r, where r is the distance from the center of the earth. Here let us take this as r. Okay, here it is 2r. So we got the orbital velocity. So first of all, let us apply law of conservation of energy. Okay, first we need to apply a law of conservation of energy at point 1 and 2. At 1 and 2. So let us see. So I can say that energy at 1, the total energy, it is the sum of potential energy at first point and the kinetic energy at first point. So let us see what is the potential energy. We know the potential energy formula is G, the mass of earth, the mass of satellite, divided by the negative sign of course, and divided by the distance, that is r. At one position it is r. About this it's half, and the mass of the satellite is m, and velocity initial it is u square. Got my point? So this is energy at 1. So similarly, if we find energy at 2, it is potential energy at second point and kinetic energy at second point. So at second point the distance is going to change from r to 2r. So the new potential will be 2r. Now let us say my satellite is approaching. See very carefully, I'm saying let v is the velocity with which satellite approaches point 2. Approaches, not point 2, approaches the orbit at a distance r from surface of earth. It's a it's a velocity with which it is approaching the one point. So I can say the mass of satellite is m, the velocity of approach is v. So from here half mv square. So we know by law of conservation of energy, energy can neither be created nor be destroyed. E1 is equal to E2. So simply gmm by r plus half mu square is equal to minus gmm by 2r plus half mv square. So from here we want to calculate this velocity of with which our satellite is approaching point 2. So first of all, this small m mean mass of the satellite. Then we'll multiply this whole with 2. Okay, so minus 2 gm by r. From here multiplying by 2, so plus gm by r plus u square, and that's it. That's our v square. Got my point? So from here you can say v square is equal to u square minus gm by r. And if you want to write v, then we can say it is u square minus gm by r under the root. So now we have calculated the velocity with which the satellite is approaching orbit which is at a distance of 2r. So we'll see now that what is the situation. This is the surface of earth. Okay, and my satellite is going to reach this orbit, and we know the distance of this orbit is 2r, okay, from the center of the earth. So we are saying it, suppose at this point we mark this as a and we know this point as 2. A satellite is approaching with velocity v, and at this point it will eject a rocket, and itself it will move into this circular orbit, and we know for moving into circular orbit it will need this orbital velocity, and orbital velocity is nothing but gm by r under root. Here r is 2r, so it's gm by 2r. You got my point? So first thing first. Now also my rocket will eject. So let us suppose that v rocket is the velocity with which a rocket ejects. Okay, so if we don't know the direction, we'll say v vector, rocket vector. Okay, so let us apply the conservation of angular momentum. So apply law of conservation of, sorry, not angular momentum, it's momentum at point A and 2. So at A point my satellite with the mass m is moving vertically upward with the velocity v that we already calculated. So anything in y-axis we call it as j cap, and anything on x-axis we say it as I cap. So mv j cap. And now after reaching point 2, my satellite will move with the velocity v0, and the mass of the satellite will be this much, because m by 10 it has removed. So it will move with orbital velocity, and that too in the x-axis direction. And then my rocket, which has a mass of m by 10, it will move with the velocity v rocket, and we don't know the direction, so I'm supposing this as vector. Got it? So from here, if we calculate, it's mv j cap is 9m by 10 v0 I cap plus m by 10 v rocket vector. Small m is the mass of the satellite. If we multiply this equation and find v rocket vector, so we'll get 10 v j cap minus 9 v0 I cap. Okay, so from here, if we want the magnitude, because I want to repeat your question here, they are asking after this the kinetic energy of the rocket. So for that, we know the kinetic energy, the formula is half mv square. So we need the velocity of the rocket, that to the square part. Okay, so from here v rocket is, that is how we get the magnitude. Okay, so from here if we find v rocket square, it's going to be 10, and value of v we already calculated, it's u square minus gm by r. From here v square, so u square minus gm by r, u square minus gm by r. This 10 sorry, this will be 100, and this will be okay. So plus 81, and v0 is gm by 2r. Okay, so we'll solve this a little bit, and we'll take 100 as a common, u square minus gm by r. 81 gm, 100 is common, so 100 will multiply here. If we solve this a little bit, then we'll get 200r as a LCM, minus 200 plus 119 gm. Okay, this is our rocket velocity, that too only the magnitude. Now the kinetic energy of rocket, if we want to find, we know it's half mass of rocket into velocity of rocket, that too square. So we have mass is m by 10, and this is 100 u square minus 119 gm by 200 r. Got it? So from here we'll solve a little bit, and 2 5s are 10. From here the kinetic energy of a rocket is 5 m u square minus 119 gm by 200 r. And if you go to your options, we will see this is our option C. I have corrected a little bit, they have mentioned it wrong. So that's it. Thank you.